looking forward to your talk. Thanks.
All right. Hello, everyone. So I'm Jess from Ghent State University, where I've been a faculty since about 2011. And I've been doing research on ALD on polymers as part of the research that I do. I've been working on ALD on polymers since about 2009. So quick outline for what we're going to talk about today. So I'm going to give you a little bit of motivation. How many people here have ever heard a textiles talk? One. Okay, perfect. So I wanted to introduce a little bit about textiles and some of the research that we do on wearable electronics, and that serves as the inspiration for why we're looking at some of these materials. And we're going to look at some of the comparable technologies that we benchmark the ALD processing to. We'll talk about ALD on polymers as well as ALD in polymers. And that's where we talk about some real hybrid materials. And then we're going to talk about some of the intriguing observations that we've had throughout the years. I always like to say that so NC State has the #1 college of textiles in the country, in the United States, primarily because we're the only college of textiles in the United States. Did we get that? All right. So it's we've got the market cornered. Now, of course, the university here has a very nice textiles department, as you're probably aware, so I'm actually very happy to be here to talk about a little bit about textiles. And so, what is research in textiles? It's a little bit more than garments. There's lots of textiles in here. The air filtration is actually probably one of the bigger markets within textiles. But when you look at a textile, so I have a material science background. I look at unit cell structures within materials, and so this is a unit cell of a knit structure. You can change the materials in there very nicely. So you can you can change the polymers that go into the fibers, and then you can twist those fibers in different ways to get into yarns, and then you can add coatings on there. And provide functionalization in there, and at the result, what you end up with is a very complex system that's very difficult to make. So this is a Nike thermal comfort garment where every knit structure within this garment is specifically designed to improve the microclimate around the body, as well as enhance blood flow underneath the skin. So these are really complex structures. There's 12 different knit designs within this. And they actually, in a factory, they actually have to stitch, or have to put all these panels together through stitches. That's a lot of the research that's involved in textiles is manipulating that system, that material system. A lot of the research is also understanding the supply chain, because we're a very lean manufacturing type of industry. And this is actually the number of process steps to make a sweater. Can you believe that? So it starts out here where you actually have, and this doesn't even include growing the cotton or growing the material that's going to be placed in here. So anyways, it goes all the way down here. And so understanding where your technology fits into the supply chain is actually a very real thing that we have to consider. So how does somebody become a textile engineer? You grew up in South Carolina, which is in the southeast United States. I have a background in chemical engineering, where I did a lot of chemical processing technologies. That got me up to IBM to do a short stint where I worked on supercritical carbon dioxide, removal of residual etched material from semiconductor devices. I then went out to work at a startup company at Berkeley National Lab for about 3 years, a year and a half before I had to go back and actually finish my undergraduate. But I worked at a startup company working on thin film depositions for erbium fiber amplifiers. Right before the telecommunications bust. So a lot of people in here probably don't remember that, but or were not aware of it because you were really young. So back in 2000 and 2001, there was the fiber optics market was really popular, and there was a huge inventory of materials, and so everybody lost their job in Silicon Valley that was in that. And unfortunately, I saw that I had the foresight to get the hell out of there and I went to Johns Hopkins where I started doing research. And one of the things that I always like to tell groups like this that are new PhD students or new graduate students is that make a list of things that you don't like to do and never do those again. I started doing modeling of thin films, and I realized that I hate modeling. So that's something that I'll never do again. I'm a very hands-on material-based person. So I got out of Johns Hopkins. I went down to NC State, which is a very nice applied research institute. Started working on electronic thin film materials and interfaces. And then I started working on those same processes on polymers. So you can imagine that ALD is obviously one of those. Okay, so this is where I'm at today. We do my research group. You'll see this at the end of the talk. We integrate materials onto textiles, electronic materials onto textiles for different types of sensors, energy harvesters, routing data, routing power, and then also we make this system. And there's lots of different types of materials. When I first started out, I had this grandiose vision that I was going to use ALD for everything. Well, it turns out that you can't. It's just not economically possible at the current moment to use atomic layer deposition. And so for me to talk to industry, which industry supports about 75% of my funding in my research group, they're not interested in things that are 10 years down the road. They're interested in things that they can start to develop right now. So we're looking at like 2 to 3 years down the road. So we started looking at a lot of materials designs for today. And it turns out that by doing this today technologies, I ended up understanding how the tomorrow technologies need to progress in order to apply them. And so that helps provide this vision for these next-gen materials. Of course, so that's only 1/3 of my research, of what I do there. So I have materials innovation over here. That's where I do a lot of the fundamental research. And then I realized that no one knows how to test these materials once you get them into and start to move them towards application. So we had to start building systems and understanding how you test these systems to make them relevant. And so it becomes very applied at that point. And in doing so, we've actually had a number of startup companies that have come out of my research group. And then, of course, I do a lot of education. So I know a couple of my colleagues here, they don't have to do education. But one thing I tell you that they don't teach you when you become a professor is how to teach. They never tell you about this. And I struggled with it for a couple of years. So this is the other thing I like to tell people, is that it's okay to struggle with it when you start out teaching, but you have to find your way. And I found my way by linking what I do in my education, which is very applied-based project technologies, into my research. And so I teach a lot of the things that I do here. I teach, and so I blur the line between my education and research programs. Okay, so materials-wise, there's a lot of materials that go into wearable technologies. These are 4 of the primary processes. I would say this encompasses probably about 98% of what you would see. The industry started out with conductive yarns back in the 70s. They primarily use them for like electrostatic dissipation within garments and clean rooms, or for workers around electricity lines. And that was the big market for this for a long time. And they never really wanted to apply their technologies within e-textiles for the longest period of time. And so they became very complacent, and they were not doing the appropriate standards testing to verify the use of these materials, the long-term use of these materials, which is what the wearable electronics market was needing. Instead, the wearable electronics market has started to go towards conductive paste, and so these are screen print materials. That usually it's about a 75 to 85% loading of metal flakes within a polymer binder material, so it technically is a hybrid material. And they just pattern these materials out. It produces a layer that goes on top of the textile, and so it actually starts to get rid of those natural textile properties and starts to ruin the microclimate. And so that's why there's new technologies that are coming up, like in conductive inkjet printing, as well as some of the things that we do that are most interested to this group in vapor phase processing. So this is my kind of like personal opinion slide about where the use of materials are in textile electronics. And so you can see the conductive yarns. This is time down here. This is about where we're at today. So conductive yarns have been losing favor in replace of the conductive base. Conductive inks, you'll see how some of our research here in just a sec on these. And then vapor phase processing is just kind of emerging within this space. And as you go from here to here, you start getting a much larger breadth of materials. So conductive yarns and conductive paste, that's typically like copper, silver, some carbon-based materials. And then when you get into conductive inks, there's a lot of organic conductive inks that you can use, as well as metallic inks. And then vapor phase processing, like what we do in atomic layer deposition, that's the entire periodic table. So you can start really making complex devices. So just as a comparison to some of these technologies, let's start with screen printing. So screen printing, who has a screen print t-shirt? I see screen print t-shirts out there. You just have to raise your hand if you have a screen print t-shirt on. If you have one, you have one. Who all here has a screen print t-shirt? I'm trying to make this interactive. You can raise your hands if you want. That's fun. Who has a screen print t-shirt? I have a screen print t-shirt. Thank you. All right. There's one person at least. I know there's a couple more because you're shy. That's fun. So there's the benefits of this is that you can make these in large quantities. It's industrial scale. It's industry scalable. I've been to screen print t-shirt manufacturing facilities in Honduras where they make 1.5 million shirts per month. That's a lot of shirts. You have not much process complexity. There's some interesting things where you have to actually use you have a screen and you have a squeegee, and you can print your image through that screen with the squeegee. So the pressure is actually quite important here. There's a lot of ink waste, and so it's not very materials efficient. So when you have a conductive ink that has 85% silver in it, that's the most expensive thing that you're going to be using. So you have to make sure that you're not wasting any of it. And screen print inks, they actually waste a lot. You can do pretty good customization of designs and whatnot, obviously. This is a rotated video, so I apologize, but this is a direct write process where I take some of those screen print inks and we can actually dispense those out of a nozzle. If we lower the viscosity just enough, we can, and this is about 80x faster than what would be in a screen print technology. There's no waste here, but there's start to be challenges in terms of like equipment costs, some of the line resolutions, and also some of the penetration to textiles can be sort of annoying. So these are some of the things that we'll start to see as we get more complex. This is actually what direct write looks like. So I always like to have good images. You'll see a lot of really cool cross-sectional images of everything. So this is a silver ink that's on a fabric. So this is about what we're looking at right here. But you can actually do some pretty cool things. So this is an ink that's encapsulated in a polyurethane material where we do pick and place of electronic devices onto these structures. But you can see that these films right here basically they guard the textile from the body, or they guard the electronics from the body, right? So you can't breathe. That material is not breathable. So we need to introduce materials in there that are breathable, that we retain some of the properties of the textile that we so desire. That's where we start looking at inkjet printing. Y'all seen an inkjet printer, right? Probably? Yeah? No? Okay. All right. This is what it looks like for your office. This is what it looks like in real life in high throughput technology. So this is you could imagine that there's about two people that could stand together that are to go between here and here. These are large tools. So if you see banners on the side of buildings, they use inkjet printing technology to make those big banners. This is it's very scalable. In the research lab, you use things like a Fujifilm Dynamics printer. You can actually print out nanoparticle inks, or you could use particle-free based inks, which are basically salts in a solvent. and then you print those out, and then you anneal it, and it reduces down into your metal particles and creates metal thin films that are very conformal onto these porous structures. So very similar to ALD, except ALD obviously has a much more nanoscale control. You can actually get really good resistance. Of course, you have to print a number of times, so you have multiple passes of these technology, or of this, to actually get good conductivity. Very similar to atomic layer deposition. All right. So atomic layer deposition, obviously, so the benefits that we look at and why we're looking at some of these vapor phase processes is that you get these fiber level coatings. The vapor phase processing, it turns out it's actually very similar to textile dyeing processes or finishing processes that are very common. You have really good materials breadth. Of course, a lot of polymers are low temperature materials, and so we want to have, so we're compatible within an ALD process for that. Challenges, of course, if we want to start to scale up, the equipment costs are pretty critical. And of course, to try to get really good throughput. Approximately, to make a good economical surface modification onto a textile, you have to be under $1 $1 US per square meter of coating. So that's the economical challenge there. Okay, but you can also pattern structures, and that's kind of a cool thing. So this is kind of the long-term vision here, is that we can actually we have these knit structures. We can coat these yarns at the fiber level with multiple layers of coatings in different orientations, so we can start actually making three-dimensional all fiber-based electronics. You have to also understand that textiles are just one part of this whole wearables ecosystem. So right now, who has a wearable electronic on them? Anyone have like a Apple Watch or a Fitbit? You do? All right. Very cool. So these are you're in phase one of accessories for wearables. They do basically, not much. We're getting more complicated as we increase the platform the areas of the platform that we can actually integrate some of these electronics. Eventually, these patches are taking over. And even longer term, we're all going to be wearing implants that monitor everything in our life. It's very Black Mirror, if you're familiar with the Black Mirror show. Probably? Okay. All right. It's nuts. Okay. So, but all of these technologies require new materials and new process development, and it's all going to be on polymers or polymer-like materials, because they have to have some flexibility and whatnot. So, as we emerge. As these wearables emerge, there's a number of challenges. Number one, the materials processing on polymers. So we have thermal limitations. We have we have to have really good materials breadth for placing all of those materials on there. We have to pattern all these really tiny devices. We have to have really good flexibility of those materials. We have to have biocompatibility of those materials. And we have to do this at a really low cost so we just don't break the bank by wanting to go out and purchase something that saves our life. So there's a lot of opportunities for ALD and ALD-inspired hybrid materials to make this work. Okay, so we're going to talk about some ALD on and in polymers. Are you ready? Right. So yesterday you probably saw systems like this, right? This is an ALD system. I'm sure you've seen like thousands of these now within the past 3 days. So this is a system that we have in our lab. So it's a hot wall flow tube reactor. You have precursors over here. They're currently not on the system, but they would go exactly right there and there. They flow gas. They flow into the system. We have a pump down here that you can't see that's actually pushing that flow. So you sequentially dose TMA, and most of the things we'll look at today are trimethyl aluminum, and then we also have the water as the co-reactant. There's the flow. Okay. So in that reactor, you can actually do a lot of things, and we have, and through time, we have developed, there's basically 3 ways in which ALD happens on polymers. There's polymers with reactive sites on the surface. There's polymers with reactive sites inside the polymer. And then there's polymers with no reactive sites, and we're going to go through each one of these. This is what happens when you do atomic layer deposition on cotton. So everybody knows what cotton is, right? Okay, see, textiles is actually pretty easy, okay? As long as you know some of the basics. So cotton's a basic. All right, so cotton has hydroxyl groups on the surface. So when you expose a trimethyl aluminum onto it, the aluminum oxide grows right on the surface. This is a cross-sectional TEM. So the way in which we make these samples is we embed them in an epoxy and then do a microtome. So this is very similar to like what you do in a lot of biological TEM. And we do a microtome slice of it, and then we place it into the TEM, and we get nice images. You'll see really high-resolution images of how we do this in a little bit. So it looks the same before and after. We get nice conformal coatings. That's typical ALD. So when you actually put something with that has no reactive surface onto it, like a polypropylene, so there's no OH or hydroxyl terminations here, you actually get penetration of the growth into the material. So so you get these island formations here. And that's distinctly not ALD, right? This is actually more of a chemical vapor deposition process. And what's happening is that at higher temperatures, you open up the pore volume of your polymer, your precursors diffuse in, and they're unable to diffuse out before you place your co-reactant, and the co-reactant just gets sucked into this polymer, reacts with it, forms these islands, and eventually you start having ALD kind of grow out on those island sites. This is actually what it looks like through process right here. So this is after 10 cycles. Kind of see some little black dots in there in this polymer fiber. So this is an epoxy out here, you see a little bit of black dots. After 50 cycles, you start to see a little bit of a surface nucleation, but it's into the surface of the polymer fiber. And then at about 100 cycles, you actually start to see some sort of what would be similar to like an ALD surface. And then from that point on, you actually get ALD. This is all happening at 90 degrees Celsius. So this is back in 2010, a long time ago now, actually. But we started seeing some pretty cool stuff. We can actually lower the temperature. So we're playing with the polymer now. Playing with polymer physics. So we can basically reduce the open pore volume of the polymer, or reduce the free volume of the polymer by lowering the processing temperature, and we can actually get conformal coatings on the surface in a much quicker fashion, or at a lower number of ALD cycles. So here's the basic mechanism. So you get this polymer fiber. It expands out because we get this polymers expand when you heat them up because of this increase in free volume. You get the diffusion. You have the reaction. It starts to expand and swell, and then you gradually have nucleation at those sites as you produce more, or as you do more ALD cycles. So we can actually use this to play with the use that lower temperature to actually produce nice conformal functional films on the surface. So this is zinc oxide. Typically, if you do it at 120 degrees Celsius, it's about 100 cycles right here. Or actually about 250 cycles, I think. And then you get this island growth in the middle. It's really kind of cool. So you can actually see all these little islands deep inside this polypropylene right here. It's pretty wild. But if you can actually do a pre-treatment layer of a low temperature aluminum oxide, so at the 60 degrees, this aluminum oxide forms a nice conformal film. And then we can grow zinc oxide directly on that, and that makes it a much more functional material. So we're going to apply these into sensors here, okay? So we can take this, and this actually turns out to have a very low conductivity, but then we can place this on, and the conductivity goes up significantly, which is good. And so we can actually use this so zinc oxide is a semiconducting material, which means that it has a band gap, has intermediate states. We can actually form a depletion layer as if we have basically illumination versus non-illumination. and we can actually see the resistance on versus the resistive off ratios goes up when we have a lower number of cycles versus a higher number of cycles, so the depletion layer is actually going more into the material. We can have much more better sensitivity with thin film sensors. Hey, that's what everybody knows about sensors. So we were able to show it with ALD. Okay. Another cool application was in photoreduction. So we have a semiconducting material, so it has band gap. So we can take our textile, we can do our coatings on it like this, and then we can do a photoreduction. So in this case, what we're doing is we have a silver nitrate that is a very low amount of silver nitrate in a solution here with water, and then we put it out into the sun, and we're going to see what happens. What do you think is going to happen? The silver is probably going to reduce onto that surface based on the sunlight energizing up and creating some excitions. All right, so what we have, so you'll see it right here. We place our samples in. This is a little bit of a sped up video, but you can see that we're actually starting to get silver reducing onto our zinc oxide coated textiles. And it goes on and on and on. And anyways, so this is what it looks like when you do that. So this has TiO2, our titanium dioxide coating, made with titanium chloride and water, and then the zinc oxide with diethyl zinc and water as the ALD precursor and co-reactants. And you can see that the morphology of the reduced material, so the silver, the reduced silver, actually is different in these both cases. In here, you can see these large dots. That's actually silver chloride. So it turns out there's a lot of chloride still left in this process, and it actually reduces out the silver chloride onto the surface. So it actually has these little tiny cracks in here that form. So that's why you get these little nice little spirals in here of these ordered structures of these silver chloride particles, and then inside there's actually a lot of like little tiny silver particles. Okay, so we can actually go and do this with a lot of different materials that you would typically find in wastewater streams. So we have chromium, arsenic. We can do combinations of those. We've done mercury. We've done a lot of different types of materials. And you can actually see that as you increase the number of cycles, you can actually increase the amount of material that you're getting out of the solution. You can also do the same thing just by increasing the amount of coated textile that you place in these solutions as well. But now we can actually do this in another way as well. So we can actually start to pattern electronics on textiles. And this kind of goes back into the wearable electronics thing. So now we're going to use the same thing, silver nitrate in a solution. We shine a laser on this. So basically we're just doing some patterning with this laser onto this material. And you can see that we're actually now reducing the silver within this pattern. So you can actually see it right here. So now we're actually writing electronic patterns onto the semiconducting coatings. So we're starting to build out these more complex structures, as you see here. We've actually got a little bit more perfected than this video shows. You can actually get it all the way through just by changing some of the textile structure as well as how much energy or how much wattage of a laser pointer they're using. Okay, so we talked about two already. It's kind of crazy. So we've talked about polymers with reactive sites and polymers with non-reactive sites. And now we're going to go and switch gears here and talk about polymers with reactive sites, but the reactive sites are kind of, it's a little bit different than this one. You'll see. All right. So this kind of dated here, but back in 2010, just kind of tell a little bit of a story here. This is one of the first samples that we did, and we did a cross section on nylon 6, or standard nylon, we found that there seems to be like this really interesting layer that goes underneath this ALD coating right here. This is the ALD coating that we would expect, and then we have this material in here. And so it would seem that our material is actually, again, diffusing in, and then our water comes in, diffuses in after it, and reacts with the material. taking it back a little bit further, these are some of the first papers that were done or that showed ALD on some sort of polymer. It's a group out of Italy, in which they were doing ALD atomic of aluminum oxide onto P3HT, and they found that there was a very so the P3HT is this layer right here. They found that there was actually a layer at that interface that was became a very rough surface. In addition, this is silicon down here. So this P3HT spun cast onto silicon. And what they showed was that aluminum oxide was actually traveling through the P3HT and was forming a layer at the interface with the silicon. Steve George's group, back in 2005, was one of the first groups that looked and started to think about a mechanism by which you have a polymer, so which is an easy way of thinking about a polymer is like a bowl of spaghetti. So you have a lot of polymer strands in here, polymer chains, and then your ALD growth is gradually nucleating from outside in. This is actually kind of what we looked at when we saw the polypropylene, where there's no reactive sites. But very distinctly, and the resolution on this videos on the images aren't all that great in this room, but you can see that there's actually if you do this on a spun cast nylon 6 material and you deposit alumina on there, you actually get very thick layers of this hybrid material that stretches into the film from the upper surface. And then we have and it decreases as we increase the temperature that we're doing our processing. So 120 nanometers here, 39 nanometers here, and there's no thin film interface once we get to a high enough temperature. So it almost seems that this is counterintuitive. I just showed you that as we increase temperature, our diffusion goes up, right? But now our diffusion's going down, or the amount of material that we're placing into this material is going down in this case. So what's happening? We'll talk about it here shortly. It is sure enough a hybrid material, so you can actually see this kind of fuzziness in there. We did a EDS in that, and we were able to find some oxygen and aluminum. So we started thinking, okay, well, how could we use this? And so we have this multi-layered material where we may be expecting that this material might have some different mechanical properties. And so this might improve the flexibility of the materials that are on top of it. And it turns out that there's been a lot of work done on how cracks form in thin films, as you can imagine, when you flex them on polymers. And so this is some of the mechanisms you can, I won't go too deep into it, but this is what happens when you do atomic layer deposition onto a lot of these thin films. And you apply the flexibility, you can get a critical tensile strain. Oh yeah. So what you do is you actually go in, it's a really tedious process on how you do this analysis. You actually go and look at the spacing in between these cracks. So this is looking top down onto a thin film, and you can actually see these cracks form, and you look and see how those cracks form as you bend it. And so if you do this, you can actually determine what is called a critical tensile strain. That's when the cracks actually start to form, and it varies with the alumina thickness. So thicker films are less flexible, right? Okay. And then it actually has is found a scale as 1/H to the 1/2. So our hypothesis going into this said, okay, well, when you have just a coating on a polymer, you're going to get energy is going to disperse out in the lateral region along this coating when you strain it. But when you have a hybrid layer underneath, it might actually, if there's really good bonding in between the coating and this hybrid layer, then you can actually disperse some of that energy vertically into this hybrid layer and get a higher critical tensile strain. And that's exactly what we see. So we can actually see that here's our crack formations as we increase in temperature. So no hybrid layer over here, much bigger hybrid layer, thicker hybrid layer underneath this material in this case at lower temperatures. This is actually what it looks like, and it actually seems like there's actually a kind of a sweet spot in the hybrid layer thickness, which actually is more of a density-related type of issue. when you have this, when you're operating at this mid-level temperature at 90 degrees Celsius as opposed to 60 or 120. Okay, so going back to this, we have this hybrid layer. What else can we do with this, or what's happening here? And it turns out there's a lot of literature that's been published on this here now, where carbonyl groups within this polymer can react with, basically you have a Lewis acid based reaction happening where the aluminum oxide, or the trimethyl aluminum, will actually react with this carbonyl group. And so this is the PA6 case, or the nylon 6 case, but there's also polyesters, PAA, PMMA. They all have different types of carbonyl groups spread out throughout the different polymers. And so there may be an opportunity to explore the mechanism of this reaction just by changing these different polymers. That's what we're going to explore now. Now, one thing that Mato Nez talked about yesterday was this effect of glass transition temperature on this process to happen. So just a little bit of polymer physics background. We're not going to go too deep into it. I know you've been here for 3 days. Basically, this is the polymer volume. When you increase temperature, you get a rapid increase in polymer free volume as you hit TG. So you have occupied volume and then you have free volume. You go from a glassy, rubbery, and then liquid states. Don't ever try to do ALD on a liquid-based polymer. Just, you can, but it's probably not going to do much for you. Okay, well, I'll encourage it. You can do it if you want. All right. Okay. One of the ways in which we're going to analyze this is through a quartz crystal microbalance. Have you all ever heard of a quartz crystal microbalance before? Some of y'all have? Did y'all talk about it on Monday? At all? Okay. All right. So quartz crystal microbalance. It's a very easy technique to understand how ALD growth happens. You can basically place this little guy here in your flow tube reactor. So this is what it looks like. You have a little crystal right there that's operating at a resonant frequency. That's usually pretty high, like 5 gigahertz or something. And then as you deposit material onto this piezoelectric device that's resonating, it will change that resonant frequency, and you can actually relate that to the mass of material that's being deposited onto that crystal. So what we do is we spin cast polymer films, and this is kind of what a polymer film looks like from an AFM perspective. When it's spun cast onto one of these crystals, and then we place it into our reactor, and we do our ALD process, and we can find out a lot of different information. And so this is what the standard quartz crystal microbalance data looks like for regular ALD growth of aluminum oxide. So you can actually see the different growth here. So you have the trimethyl aluminum reacts onto the surface right here. So this is basically on an aluminum oxide surface right here, or on a hydroxyl terminated surface at this point. You have the TMA reaction, you do your nitrogen purge, you do your water dose, it reacts, then it purges, and then you repeat that cycle. And you can see this linear pathway. That's very evident that you have atomic layer deposition going on. And then you have this is the different mass gains at each one of those cycles as you go from 0 cycles all the way up to 50. So it's consistent throughout. Okay, so this is what regular QCM data looks like on aluminum oxide. This is what it starts to look like when you start doing it on polymers. And this gets pretty tricky right here. So you start to see that after you get to so many cycles, so this is 50 cycles or 100 cycles right here, I think. After so many cycles, you start getting nice ALD growth on the surface, but it's all this stuff that's happening in between where we're wondering what's happening, where we see a lot of huge mass uptakes. We have large mass release from this polymers as well as we do our purge states, or our purge steps. And so we have we want to try to relate this to the polymer free volume here in a second. So let's go ahead and change things up a little bit, and let's do sequential trimethyl aluminum dosing. So in this case, we're not doing ALD growth here, okay? We're just taking our trimethyl aluminum, and we're going to dose it 10 times, all right, in 0.2 second doses. So we have these TMA doses here. No water is involved on this, in this case, okay? No water. So we have mass uptake. So if we do aluminum oxide, we do our first dose of trimethyl aluminum, and then the sequential doses don't really do anything. There's nothing for the trimethyl aluminum to react on at this point. It's already self-terminated. So when we have all these different polymers, we start to see different effects. So we get this huge mass uptake with the nylon 6. Then we get a gradual mass uptake with the polyesters. PMMA, we get the same thing, but a little less. And the PAA is a lot like the aluminum oxide. So you can actually start to see some possible relationships here. Number one, our TG is increasing. So our TG is really low here. And it seems to be actually the lower the TG, the more material that you're infiltrating. But then we can also start to increase the number of carbonyl groups within our polymer backbone repeating unit. And then with PMMA, we have our carbonyl group on a functional end group. And this is actually what it looks like if you start to look at the mass absorbed of the TMA as you go through as you change the reactor temperature. And these different regions, so this is operating at 60 degrees. This is the reactor temperature is gradually changing. This is the mass uptake. So the closer that we are to the TG, it seems that we have an increase in the total infiltration of this material. So then we can start changing some of the polymer component, or the polymer backbones and the polymer functional end groups within the same polymer series. And this tells us more information. So this is the TG of these two polymers, PBT and PET. You'll notice that the polymer chain is a little bit longer here. The repeating unit is a little bit longer here by to these CH2s than the PET. We actually get a much higher increase. We can also change the functional end groups, the length of those functional end groups. And we can see that, again, this is operating at a parameter of a temperature of 60 degrees Celsius for our reactor. And so here we are in a relationship to where TG is for each one of those polymers at that temperature. So you can see that at PMMA, or PEMA, we're pretty close to the TG, but with these two, we're actually above the TG. So we're getting a much higher infiltration just on a single dose. So here's what's happening, just long story short. In the PMMA series, where we have these longer functional groups, we can actually, we have a less densely packed polymer. Because these functional groups are actually kind of distorting the order of those polymer chains. And that's why TG goes up. So you can actually have these TMA molecules can diffuse further into these materials they can diffuse further into the materials into the polymer. With the polyester, where we have the functional groups on the backbone, they can again diffuse further with the larger spacing within the polymer backbone. So this is what happens when you do 100 cycles of TMA, or 100 doses of TMA on PET. Again, in a quartz crystal microbalance. You have this huge mass uptake, and you'll see that it actually does gradually saturate. And it actually saturates at a pretty high mass level. So I know that you have a hard time understanding what 8,000 nanograms per centimeter squared is. I'll give you some context here in a second. So that was actually the question that I asked a couple of my researchers in the group. Was, well, number one, how can we manipulate this? But on a more fun level, how much precursor can we possibly get into this polymer? And it was pretty surprising. So this led us into infiltration and understanding infiltration mechanisms into polymers. And this is distinctly not ALD. The polymer, or the precursor gases are diffusing in, they're reacting, and then some of the gases and some of the products are actually diffusing out. There's two really good review papers There's Lang and Lesego, and there's also a Parsons paper back in 2013 that actually talk a lot about the different mechanisms, and I would encourage you, if you're interested in this, to go and read both of those articles. So there's, again, two processes happening here. There's a diffusion process where there's bulk diffusion of your reactant materials into the bulk of the material, and then we have a reaction, and it's really as a balance between these two things. If you have a polymer that's very reactive, it will actually, like in nylon 6, it will actually stay at the surface. And it will prevent further diffusion in later on or after in more exposure of your precursor. If you have a less reactive polymer, basically ones in which or you have a more free volume based on your polymer structure, then you can actually get more diffusion in, and it will react within the bulk of the material. So these are 4 processes that have been designed, or actually 3 processes that have been designed based on atomic layer deposition, in which you have different sequences of precursor exposure, followed by a purge step, followed by your reactant gases, and then how these things work. So we'll kind of go into show each one of these individually right here. So, of course, Meidonez has created a process way back when now, right? So on multi-pulse vapor infiltration, they've worked on a lot of biological materials and understanding the hybrid structures that process into there. And looking at so this was actually on some spider silk, which they deposited some aluminum oxide into and TiO2, and found some very interesting mechanical properties of those materials. In another process called sequential infiltration synthesis, this work out of Jeff Elam's group at Argonne National Lab. They were actually create selective pattern structures using block copolymer systems in which you have a polystyrene and PMMA. The polystyrene allows for the precursor gases to diffuse in, react with the PMMA inside the surface, and then you can get rid of the polystyrene and leaving these nanostructured assemblies. My group, as well as Greg Parsons' group, has worked on a process called sequential vapor infiltration, in which I kind of think about it as a 2-step batch process. You have an exposure of reactant A. You let it sit in that for an elongated period of time. We can actually continue to dose materials in there, or dose the precursors in there, or different precursor materials, and allow for basically the reaction to come to completion. And then we expose our second reactant, like water, into there as well. And it turns out that there's a lot of different things that are happening here. So at different temperatures, you can actually get different things to happen, and we'll kind of explain that as we go through this. But we have an infiltration, and there's a Lewis acid-base reaction in which the aluminum oxide, or the TMA, is reacting with the carbonyl groups, of course. So if you think about it from a processing standpoint, we have an untreated materials here. You can also think about this as flexible thin films. We take it into a chamber that has our organic metallic vapor. We can then do an inert purge, and then we can shuttle it through this, and then we basically finish up whatever reaction is happening with a co-reactant here. And then we have our treated fabric at the end, or treated material at the end. So you can think about this as a continuous process very easily. And there's a lot of different ways in which you can look at it. This is a batch process. It's very similar to how we do it in our flow tube reactors, but then there's a lot of roll-to-roll processes that we can imagine here as we move forward. So this, again, towards the thinking that we wanted to see how much TMA we could actually react into these materials, we took fabric samples, we weighed them before we placed them in the reactor. We did a number of different exposures to it, and then we, at different processing conditions, and we weighed them after. And this is a percent mass gain on these materials. You can see we get up to 10% here, 16% here, and you can actually see that there's different At different dosing levels, we can and at different reaction temperatures, we get different processes to happen. With PET, we see similar effects on temperature, but if you actually look at the effect of exposure, they all kind of follow the same line. Mind you, that's 110% mass gain. So that's actually literally doubling the mass of whatever fabric I'm placing in there. That's actually a lot of TMA I'm putting in. First time we did this process, we placed in the reactor, we exposed a lot of TMA to it, and we didn't do the water step afterwards. So we purged everything out. We took the sample out, and it literally caught on fire. All right, it was really impressive. There's a lot of TMA in there. Don't do that. Okay, so this kind of tells us a little bit about some of the influences about what's happening here. And so with the nylon 6, we do our TMA dose, and it actually self-terminates at the surface, and we get and it limits the total amount of subsurface reaction as we go up in temperature. There's at lower temperatures we get more infiltration. At higher temperatures, because it's so reactive, we actually get closer to ALD growth. In the PET case, the polymer volume is so large that the TMA can actually go in and infiltrate all the way into the middle of this material, and then the reaction gradually occurs as we can and completely modifies the bulk of the polymer as we expose more TMA to it. The interesting thing is that we know that this is happening. We form these complexes here, but what we are very intrigued about is, and what would make this a hybrid material, a true hybrid material, is if we can get these coordination complexes to happen. Maydonez actually, within some of his work, had talked about this within some of the biopolymers, and so we were very interested to see if we could actually do this with natural polymers as well, or not natural polymers, but synthetic polymers. So this leads us into organic, inorganic hybrid materials. Okay. So what would these be used for if we can actually make them? There's been a lot of work out on hybrid materials, obviously, where there's a lot of electrochemical, optical, mechanical, electronic applications, catalysis. You can do some biomedical stuff with it. And people have been making this with sol gel or metal organic frameworks for some time. But it would be really kind of cool to do this with MLD and some of the infiltration techniques. And so we're looking at the infiltration techniques here. So this is on PBT, so it's polyester. So that polyester, remember, it's open enough, that pore volume's open enough that I can actually diffuse all of my precursor in, and it completely modifies the material. So we take a PBT, polyester polymer, and we go and we do our process, and then we burn out, and then we anneal it at a high temperature. We can get rid of all of the organic component and just leave our mesoporous oxide structure. And this is what it looks like. And so this actually confirms that it's actually diffusing all the way in and reacting with the entire material. We can dump nanoparticles in here if we want to, and the nanoparticles actually kind of diffuse into that hybrid material. And it actually forms very nice cages around. So this is actually the burned out polymer again with the nanoparticles, and we can the metal oxide framework that goes around it actually produces a cage, kind of a nano cage that we place around the nanoparticles, and it actually increases the temperature by which, or it prevents the nanoparticles from migrating together and coalescing as we anneal those nanoparticles. So kind of an interesting application right there towards high temperature catalysis, which you use a lot of gold nanoparticles for. So this is thermogravimetric analysis. Anybody ever heard of TGA before? Probably. Okay. So here's the heating rate at 20 C per minute under nitrogen flow. Basically, we're starting to get rid of all the material, or it's oxidizing and evaporating. And what happens here is we actually get these extra peaks as we start to see more of this infiltrated material, and we can know that this is a distinctly different material that we've seen before. So this is the original polymer, and this has this nice. We're considering a higher temperature hybrid material. So when you actually do this on fibers, you can, so this is a PET, single fibers. So this has a fiber as when you draw out a fiber, you draw them out as filaments, and these draw ratios, so you have these drums that are pulling this melt fiber out, and based on the speed of those drums, you can actually increase and decrease the crystallinity of the polymer fiber. So this is technically what a polymer, inside a polymer fiber, about what it looks like. You have these crystalline regions right here, and then you have these amorphous chains that link in between these crystal regions. If our hypothesis was correct earlier, where we kind of discussed these complexes, then we would imagine that in these very loose areas of these amorphous regions, we can actually start to form these linkages or these metal-coordinated complexes or interchain complexes that go in between. And this would actually, so this is the original control fiber, and then as we manipulate, or as we increase the number of trimethyl aluminum cycles into this at 100 C exposure, we can actually see some increase in strength as well as elongation. And so this would be an indication that we are actually seeing these interchain complexes. Okay, so interesting observation. Number one, when we used to take out all those samples, we would see it catch on fire. I talked about that one. The next thing we would see is after we did the TMA, or after we did our water exposure, we started to see color changes within these materials. Being a textile person now, I like how textiles are dyed, and the diffusion of the dyes into the polymers are very similar to what we're trying to do with our infiltration techniques, where we manipulate the temperature by which these dyes can actually move in. So it was very interesting for when we increased the temperature, we actually started seeing what we would think of as dyeing of these materials into different colors. What's even more interesting is that it actually had some very interesting optical changes when you put it under a black light as well. It started to have some luminescence. So we decided to explore this. And we actually saw new peaks forming when we did these higher temperatures where we would expect that we would have. And this is actually very similar to some of the peaks that you might see in yellow dyeing or yellow dyes for textiles as well when they react with the polymer. From an optical change standpoint, again, this is PET. It's kind of actually interesting. PET, because of the pi electrons here in the backbone, it actually has a small photoluminescence to it. So here's the photoluminescence peak, photoluminescence spectra as you change the wavelength of untreated PET. This is what happens when you do your infiltration and reaction into the material. At lower temperatures, you actually get a very intense photoluminescence peak increase, and then at these higher temperatures, you actually start to get something that seems like it's a little bit different. The wavelengths actually, or the peaks are a little bit different here. What's happening is that you can actually, since these pi electrons exist, once you start actually adding a metal ion that's close by to those, you can actually get photoluminescence to increase around those pi bonds. And so we're taking advantage of that now when we start making these hybrid materials. And again, it's evidence that we're getting these interchain complexes. So we can actually do some patterning. We've done some work where we do this at atmospheric pressure as well, where we do masking on here, and we can actually get some pretty good resolution within our mask designs when we do this. Going a little bit one step further, we can do some photoluminescence excitation spectroscopy. This is where you basically you pump light into a material, and then you you pump energy or photons into a material, and then you wait for the excitation to happen at certain wavelengths that are a little bit lower. And this would be, if this actually happens, this would be an indication that you have what would be like a semiconducting or organic semiconducting material. And sure enough, this is what we see. At 90 C, we actually see basically these two peaks right here, at 424 and 450, these right in here, and then at 150 we actually see two distinct peaks right here, indicating that we have maybe a multi-layers as we go into the material. So one type of structure in the inside, another type of structure on the outside. It turns out that we actually have a pretty incredible amount of internal quantum efficiencies, which means that the materials that the energy that comes in is actually being utilized in an effective way. So for a polymer to have 25% internal quantum efficiency is pretty good. The absorption here is actually increasing as we increase the temperature here as well. So now I can kind of go into doing a little bit of the same stuff that we were doing earlier. So we have this photoreduction of these metal atoms. Now that we have, this is now just a polymer that has infiltrated trimethyl aluminum. We don't have, earlier I showed a semiconducting material, zinc oxide. So again, we shine light in. We want to reduce the silver. It turns out that once we do this infiltration, we can actually get a nice silver. We can do gold fabrics, which are really expensive fabrics. We can do arsenic on these, which are really deadly fabrics, and whatnot. So just some X-ray diffraction showing that we can actually get those materials. And this is some of the TEM showing the, or SEM here showing some of the nanoparticles that are generated on here. We can go in and mask this through flood exposures. So we can actually put a mask on there, do a flood exposure. We get these nice patterns of written electronics or of electronic structures now on this material, and then we can do the same approach that we did earlier. And it's actually much more efficient than the semiconducting materials that we had shown for the zinc oxide and TiO2. Okay, so quick summary. That's a lot of slides in an hour and 15 minutes. All right, so we have our polymer fiber. There's a number of different types of mechanisms that are happening here. I'm actually now breaking the infiltration into two things here. But generally, you have ones with reactive surfaces, you have ones with non-reactive surfaces, and then you have ones that are really reactive but still allow for a little bit of infiltration, and then ones in which you have complete infiltration into the polymer because of the high polymer volume. In terms of things, you always have to understand where your technology is versus these other things, and so that you can start to, or based on other ways in which you could do similar types of processing. And that helps you understand the where it's going to end up being applied and the usefulness of where it would be applied. So this is a lot of the things that we try to do in my research group is we look at all these different technologies, we look at them how they might be economically applied into all these different technologies, and of course these hybrid structures are the key. So this is my research group from about a year and a half ago. In fact, actually had a couple people leave. Allison's at Flex now. Raj and Hassan, they started their own company. And Jack, he was a master's student. He's a graduate student now up at New York University. And I've got another couple people now are in the group. But again, about 75% of the funding comes from industry. So if you want really good industry funding, you have to make it relevant to what they're doing. Okay, so with that, I'd be happy to take any questions.
Thank you very much. Any questions?
I'll be here afterwards as well.
Yes.
So you mentioned about the time, the temperature for this reaction, that the temperature less than 150 is good, that no degrade of the polymer properties obviously.
That's right.
So how is the time and pressure required for the reaction?
Yeah, so the time and pressure required for the reaction. So that was some of the things that we were doing with some of the dosing. So you can, that's a tough question, especially when you're trying to, when I'm thinking about SVI, so I'm trying to get my head wrapped around it a little bit. So you have to apply enough precursor into the reactor in order to saturate into that polymer, right?
Yeah.
And a lot of times that requires continuous dosing. And so it's very difficult to put a time scale on these reactions. You can always limit the time and just by limiting the dose, the amount that you dose. And that's going to influence how much of the reaction you've done inside the material. Does that make sense?
Yeah.
Okay.
And how is pressure?
The pressure is, so we have had a couple papers out on pressure. It turns out that the infiltration can still happen. It's just that the diffusion of the gases in and out are going to now be altered by the pressure just because of the, we're basically, we're adding a lot more nitrogen. So the, yeah, it's not, we're not really under vacuum. So the gases can't, or the molecules can't really travel very far into the polymer in some cases. So it requires a longer term saturation.
Yeah. So it means that it's kind of high consumption of the precursor gases, yeah?
Yes, very high consumption, yes.
Yeah, so, and it makes expensive.
Yeah, yes, it does actually make everything very expensive, especially when you do this at atmospheric pressure, because you have to flow so much nitrogen into the systems. So yes, looking at ways in which you can economically and efficiently use the materials is definitely an area of interest. That's something that we did. You know, I would have to say that we have never done the calculations on the efficiency use of the TMA within these infiltration processes. We actually did a back of the envelope calculation one time. That's pretty boring. Yeah. As you can probably imagine. But of course, that's going to, if you change reactor designs, you can alter that significantly. And so we're using pretty much the worst case scenario in terms of reactor design for this process.
All questions?
So, of course.
Just a curiosity. You had this comparison of SIS, SVI, and MPI processes.
Yeah.
And you showed in the MPI process no purging steps.
Was there not a purging?
No.
There's no purging.
So there is most likely a mistake in your sketch.
Yes, there is a purging step at the end. Yes. Yeah.
No, not at the end. In between.
Oh, in between. Okay.
In between the precursors.
All right, I'll have to go back and look at that figure. Okay, thanks. Okay.
Other questions?
So if you do MLD of like a metal cone, you use TMA and an organic molecule,
Right.
can you also expect infiltration of the deposited MLD film by the TMA molecule?
Yes, I would imagine that you would. And I think that we talked about that a little bit yesterday. That I think that there's some information about how the TMA is kind of is going into those materials. So yeah, I would imagine it would. It's got to be. I mean, a lot of those images when they talk about some of those MLD films, I mean, it's pretty close packing of the organic materials that are being placed in there. So it's really dependent on that. It's sort of close packing.
So do you think of a way of combining actually doing a traditional textbook MLD deposition layer by layer growth and SVI or MPI or whatever three-letter abbreviation was used?
Yeah, absolutely. So I mean, if you even look at a lot of ways in which there is vapor phase deposition of organic semiconductors, I could also imagine a lot of the same ways that, I mean, just like in P3HT, that was a vapor phase organic deposition, and they were able to see the TMA travel all the way through that. So that's kind of one step towards that, no doubt.
Maybe also towards for the benefit of the students, I think when it comes to reviews, there's also a very recent review, July 2018, I think, in MRS Bulletin that maybe is also worthwhile to look into if you're interested in these types of topics. And MRS, communication, and so it's definitely an emerging field and a very interesting domain to work on. Very relevant, I think, also for that. So thanks a lot for your very nice talk. Before we go to the sandwich